Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In this video, we're going to talk about a very popular and common language in data mining and machine learning. We're going to talk about supervised and unsupervised learning, and we're going to see what everyone means when they talk about supervised learning versus unsupervised learning. Alright, let's look at the slides. Alright, after a few recap, we're going to talk about this language, supervised versus unsupervised learning. And after that, we're going to talk about another new concept. The concept is Metric Optimizing Supervised Learning. And towards the end of the video, we're going to talk about Semi-supervised Learning, which is a very different concept, but since it's similar to supervised and unsupervised learning as far as the names, I will also include that in this video. Alright, so the recap we're going to be about prediction, classification, and clustering. In prediction and classification, as we've been seeing throughout our videos, is that what we are trying to do, we are trying to find the relationship between a set of independent attributes and a dependent attribute. By finding those relationships, we are hoping to be able to predict or classify the dependent attribute. And this is what the algorithm for prediction does. And the only difference between prediction and classification, of course, is that the classification target is categorical, while prediction is numerical, right? So that's the only difference between these algorithms. But then when we get to clustering, we don't have a dependent or target. We don't have a dependent attribute or target. And clustering runs by having no target or having no dependent attributes, and basically tries to find the inherent patterns as far as the similarity between the data objects, similarity and difference between the data objects based on those attributes. So this lays a good foundation for our conversation about supervised and unsupervised learning. But let us start from the ground. What is learning? So learning in the context of language, in the context of human learning, is basically having knowledge and having practice to become better at a task, right? So that's what we mean by learning. When we improve in a task, we talk about learning. But what does that mean, this term learning, in data mining and machine learning? In data mining and machine learning, when we talk about learning, what we mean is the estimation of the parameters of a model, right? This model could be linear regression, multi-layer perceptron, it could be decision tree. So any model that we have, they do have parameters and some flexible parts. And once we start training them, or the model start learning, basically those parameters, which could be weights for multi-layer perceptron, could be a coefficient for linear regression, we estimate them. And this process of estimation can be known as learning. So for example, betas for regression model. The regression model learn by estimating betas, or the weights for ANN, or multi-layer perceptron, which is another name. The MLP, with the one that we learn, is a specific type of artificial neural network. So now, by this knowledge, let us move to the distinction between supervised learning and unsupervised learning. And the distinction is, supervised learning is trying to improve the prediction of the dependent attribute or a target. The best and easiest distinction between supervised learning and unsupervised learning is to see if in your process of learning there is a dependent attribute or a target involved. And if that's not the case, then you have unsupervised learning. While during the process of supervised learning, we are trying to do our learning to be able to predict a target, for unsupervised learning, our goal is to discover the inherent patterns of the data, right? So these are the differences between supervised learning and unsupervised learning. And the distinction could not be simpler. The only thing you need to look at is that does your algorithm need a target or a dependent attribute? If it does, it falls under supervised learning. If it doesn't, it falls under unsupervised learning. Let me take one more steps as far as conceptualizing these types of algorithms and these types of learning. A supervised learning can also be categorized or be classified into two other types of learning. We can have metric optimizing supervised learning, and we can have non-metric optimizing supervised learning. And the distinction between them is very important. And the importance of it comes back to us being able to use machine learning algorithms, data mining algorithms in a more ethical way. So during this video, we might not be able to actually get to that fact that how knowing about metric optimizing and non-metric optimizing is going to be influential for ethical machine learning or fair machine learning. But let us build the groundwork, and in the next video you're going to see how that's going to matter. But what are these? In metric optimizing supervised learning, as you remember, when we are talking about supervised learning, we're talking about being able to predict a target. And when we classify a target, we're basically predicting two, right? And a metric optimizing supervised learning is one that goes about finding these relationships with the purpose of optimizing a specific metric. And that is why we call it metric optimizing. And there are some other classification, there are some other supervised learning that they don't have such goal, and we're going to see examples of those. But before we see a couple of examples, let me tell you where this language comes from. If you were to Google metric optimizing supervised learning or non-metric optimizing supervised learning, you're not gonna come across a whole lot of different material about it. This specific material or this specific language comes from my own paper that was recently published in Neurocomputing. And then the name of the paper is Supervised or Unsupervised Learning, Investigating the Role of Pattern Recognition Assumption in the Success of Binary Predictive Prescriptions. There are a lot of things going on in this paper, and one of the things that this paper has introduced and has contributed to the literature is this language I'm talking about here, the metric optimizing and non-metric optimizing. So now let's talk about different algorithms that we learn, if they are metric optimizing or not. Linear regression, if you remember, it has an equation, right? So the equation for linear regression is, for example, the target is equal to beta 0 plus beta 1 multiplied by predictor 1 all the way to beta n predictor n, right? So in this spectrum of metric optimizing, supervised learning, and non-metric optimizing, so from now on, let's call this MO, let's call this NMO. Linear regression falls under the non-metric optimizing. Pay attention here that I am not using a binary, this is metric optimizing, the other is non-metric optimizing. The reason is this is a spectrum. One algorithm may be, both algorithm may be metric optimizing, but one algorithm may be more metric optimizing. And we'll see what I mean by that. And the standard linear regression that we have been using and we have been learning about, it's an example of non-metric optimizing. The reason is the algorithm does not try to maximize accuracy or any metric. It tries to find the relationship between the independent and dependent attributes. And then once those relationships are found, then we use that for prediction. So the goal is not to predict, the goal is actually to find relationships. It does not mean if we have an algorithm, right, that uses this equation and uses an alternative way to find these betas, and in that alternative way, the goal of finding these betas are to maximize a metric. In that case, we are not using regression, we are using another new algorithm, and that could be a metric optimizing, right? What I mean by non-metric optimizing here is a standard linear regression that we use the least square error way to find these betas. So that's linear regression. Now let's talk about K and N. Let's think about if K and N uses any metric to optimize itself, or it's just the way it works is trying to find the wisdom of the neighborhood. Do you remember it tries to find the neighbors and then see what's happening around the neighbor, and then it comes to a result, right? So that's K and N. If we have a naive K and N, by that I mean we arbitrarily select K. So we select this arbitrarily, right? If we select this arbitrarily on the spectrum of metric optimizing and non-metric optimizing, the K and N will fall under here, right? It does not try to optimize any metric. At no point during the algorithm we have that goal. But if we go about finding K in a tuning process that tries to optimize a metric, right? So remember, when we were tuning K and N, sometimes we'd use accuracy, F-score, different things to find that one. Then the algorithm shifts a little bit. It does not become the most metric optimizing, but certainly this version of the algorithm that we tune K for a specific metric, it becomes more metric optimizing than the one on the above, right? So this is a really good example to sort of see how this is in a spectrum. This is not a binary metric, either metric optimizing or non-metric optimizing. Naive Bayesian. Naive Bayesian also in this metric optimizing, non-metric optimizing falls under non-metric optimizing. Again, naive Bayesian, if you remember, it uses conditional probability to just find the naive conditional probability of a new data object, and at no point does it try to maximize any metric. So it's one of the non-metric optimizing supervised learning. How about decision tree? Decision tree, where does decision tree falls under this metric optimizing and non-metric optimizing? Decision tree is more towards metric optimizing. Remember, when we were going about decision tree, how would we choose what attribute to use for the splitting of our data? And then how do we choose for the numerical attribute to find the best split? We will split to be able to have more purity. And when we are moving towards more purity, in direct ways, we are trying to improve our accuracy. It's not completely direct to try to improve accuracy, like the next algorithm we are going to talk about, which was MLP. But here, there is that effort from decision tree to move towards this purity of decision tree, purity of the leaves, and that is somewhat metric optimizing. So it's certainly towards more metric optimizing. How about MLP? MLP, among all of the algorithms that we have learned, is the most metric optimizing. If you remember, MLP specifically uses error to reduce the error, right? So it uses a feedback loop to be able to come to state that it has the least amount of error, and it uses error to learn, optimize that. And because the error is, the metric that we are using to minimize or change the algorithm, that is one of the most metric optimizing algorithm that we know of. So now let's compare all of these together, right? So we did talk about a couple of algorithms here, right? Non-metric optimizing. We want to see what are the relationship. So NLP would land here, the most metric optimizing, and then we would have decision tree here, and then we would have KNN, K tuning, we tune the K, and then we'd have KNN. Actually, the last one would be all of them the same. It would be KNN naive, K arbitrarily, then would be naive Bayesian, and then would be regression. I mean, we don't have sort of like, a way to be able to distinguish between which of them is more metric optimizing or not. That's why we say all of them are more towards the non-metric optimizing. Alright, before we finish this video, let us talk about this other concept, semi-supervised learning. While the concept of semi-supervised learning is not really connected to unsupervised or supervised learning, it's basically a concept that is about specific types of data sets that some of the data objects in your data set are labeled, or you do have the target for them, and some of them don't have the target for them. And in those cases, one of the ways you can do a supervised learning is by discarding all of the data objects that do not have a label. And that would be just a supervised learning. But there is another way to go about that, and that is called semi-supervised learning. And the wisdom behind semi-supervised learning is, why should I let go of learning about these data objects that are not labeled? How about I try to find ways to still be able to improve my prediction or my classification by somehow including the information that these unlabeled data objects can give me, right? So I'm not talking about the details of how an algorithm goes about this. I'm just trying to give you a distinction between supervised, unsupervised learning and this other concept, semi-supervised learning algorithms that somewhat very different than these two other concepts, but they have similar names. So I wanted to make sure that you do see the distinction. Alright, in this video we talked about supervised and unsupervised learning, and then we talked about the importance between metric optimizing and non-metric optimizing supervised learning, a concept we are going to heavily use in the future video, that we're going to talk about ethical data-driven decision making. And then we talked about every one of the algorithms that we've seen so far, KNN, naive Bayesian decision tree, NLP, regression, and we saw where do they land in the spectrum of metric optimizing and non-metric optimizing supervised learning. And in the end, we talked about semi-supervised learning and how it is different than supervised and unsupervised learning. Until the next video.